the wrong screen. You see the presenter screen or the actual slides?
The actual slides. Yeah, we see the actual slides.
Okay.
And
okay, that's good.
They look very impressive. So.
Okay, great. Okay. Yeah, I cannot see anything else. Okay. Should I start?
Yeah. Great. Caterina has agreed to replace Muli Sagiv, who we're still waiting on, and Caterina has been doing a lot of really interesting work with static analysis and machine learning. So look forward to her.
Okay, thank you. Well, this talk is really mostly work in progress. I mean, towards the end, I will mention some things that are done, but it's just some things I've been working on with some students, some interns, some ideas that I have that are still not done, but yeah, sort of in this area. So what I'm trying to develop is a static analysis for data scientists. So this data scientists are these people that are sort of in the intersection between the mathematics, statistics. They have some computer science background and IT, and they in particular have a specific domain knowledge. This could be maybe economics or biology or medicine or what's not. So they what they do is really they take essentially data that is available in some form, and they process this data. So they're not software engineers, but they do, or not software developers, but they do have to write software nonetheless, essentially all day. And the software, what it does, it takes data and sort of manipulates it and processes it. So the kind of data that they write, the kind of code that they write is organized in pipelines of code. So there's sometimes very complex pipelines that take data from some databases or from data sources, and they have to clean up this data, prepare it in some way. And maybe data comes from different sources, so they have to merge this data and so on and so on. And then this data is prepared and then used in some way. So used means maybe used to train some machine learning model, or maybe just used to make some decisions in some way. And so when they develop these pipelines, most of the time, a lot of the time, this code that they write is really just to be used one time and be done with it. So they don't necessarily test it that much, they test it a little bit and it looks good enough. And then again, this data is organized in pipelines. So anytime something changes along the pipeline, maybe the database returns something different now because it has been updated, or maybe some data source now changes the format of the data that they return, anything can go wrong. So yeah, the moment we have this kind of software written by not necessarily expert software developers, things can go wrong. There are bugs and so on. And the interesting thing about these bugs in this kind of software is that oftentimes there can also be like sort of silent bugs, in the sense that the pipeline works fine, returns a result, and if the result looks plausible enough, nobody notices that something went wrong. So this is not necessarily a software error. I mean, it was related to not a coding error, but so what happened was recently, 2 years ago now, but in the UK, so they were collecting positive COVID results in some CSV files in the laboratories, I think, and then the CSV files were sent to NHS so that they could then trace contacts and send the contact alerts. What happened was that at some point they had so many cases that this file, the CSV file, got pretty large. This was open in Excel, and the CSV file was organized in a way that data was organized in columns rather than rows. So they had many more columns than rows. And essentially, when opening this with Excel, a lot of this data ended up being dropped because the file size was too big. And so a lot of the cases just went missing and contact traces were not reported. So this was just one simple case. Data was just simply dropped accidentally. There were some other cases that I found a little bit looking online. There was this this article years ago now about software used in criminal justice. So the software turns out that it was biased against some minorities. So the idea, the software was supposed to estimate the risk of recidivism, and it turns out there was newspapers and news articles and so on this. So it turns out that the software was biased against Blacks. Some other people later on actually revisited the way the data was prepared for this analysis, and it turns out that they actually had made some mistakes in the data. Coincidentally, the conclusions were still okay, but sort of by luck, because essentially they had kept around some data they were not supposed to keep in part of their analysis. Again, just because of some data processing mistake. Everything, the processing went fine, and nobody noticed until somebody tried to reproduce the results. There is also another paper that collects several stories in, I think it's mostly medicine here or biology, in which there was a lot of data processing mistakes that turns out that in some cases, the conclusions published in some papers were completely opposite of the real thing. And so they had to retract papers and redo the analysis and so on and so on. These are all examples of silent bugs that all come from some data processing mistake. So what I'm particularly focused on these days are one kind of software that is used for data processing, which are Jupyter notebooks. So these are essentially an interactive web-based platform in which you can write code, you can have visualization, you can write text, and you can sort of iteratively modify your code, rerun the code. It's organized in cells, so you can write code in different cells and then run the cells in different orders depending on the kind of analysis or explorations you're doing. So it's, a lot of the time this is used for prototyping. And so you would think, well, prototyping we don't care so much that this code is correct. But in fact, in a lot of companies, it turns out that it's actually also used in production. So there are Netflix is a big example, but there are other companies, and also, I mean, some random people on Reddit. It was a thread discussion. They said that they are in a company with a lot of employees, over 120 data scientists, that they use notebooks in production. So it's a fun, sort of different kind of platform to analyze, and since it's used in production, we thought it was fun to look into this. So I'll give you some examples to see what kind of problems you get in this kind of software. And so the first examples, I borrowed them from this paper, this recent paper, and then I have some more that I will use for the rest of the talk. But I will get back to this first example later on at the end of the talk. Actually, I don't know if it's readable, but if not, I will just get through it anyway. So don't worry too much if you cannot actually read the code. But the idea is that here we are reading some data from a CSV file. We are storing it in some variable D. Then we are transforming this data. We are normalizing this data in some way, storing the normalized data in X. Then in a different cell, we are actually overriding X by reading some other data from another data file. And then we are taking this data that we stored in X and we split it into a training and testing set and use it to train some logistic regression model. So this is sort of all the cells that we have in the notebook. And now let's say we execute this notebook and we read them all, we execute all the cells one by one. What happens is that since we are in the cell in the middle, we are overriding data that we have previously normalized by reading some other file. It turns out that we are not actually using the data that we read first. So this is, maybe it is intended, maybe not, but there is data that remains unused. This data that is read and remains unused. So I will get back to this problem here later on at the end of the talk. Other kind of possible mistakes that we make are, well, let's say now we realize that we are not using the data, so we skip the execution of the cell that overrides the data. So now we are reading the data, we are normalizing it, and then we are using it to split into training and test set and so on. Now we have this problem that is called data leak. So what it means that there is so the normalization is actually using the distribution of the data. So we are actually using some information on the testing set. So some information on the testing set actually leaks into the, some information on the training data actually leaks in the testing data because of this normalization that is done before splitting into training and test set. So we have this data leak. So now let's say we want to avoid this. So we are not going to do the normalization before splitting. So let's say we have done this, we realized the mistake. So we now re-execute the cells. So we re-execute the reading, we split, and we train. Now what happens is that, well, we had already executed the normalization before. Now we are skipping the normalization, but we are just reading the data and storing it to a variable D. But for the splitting, we are using the data that was stored in the variable X, which was the data that we normalized in the previous run of the cells. So since we haven't, so in the notebooks, we have this clear, all, forget everything and rerun. If we haven't done that, the data that we had stored in X would still be used here, and we maybe would not necessarily realize that we still have a data leak because we're using data that comes from a previous execution. So these are sort of very common issues. The authors of this paper actually have done some more work later on, actually this year, trying to detect data leaks. What we are working on is actually something slightly different. So what we realized is that a lot of the time, the problem actually comes from data that is not expected by the code. So, I mean, in the comic that I had at the beginning of the talk, the stick figure asks, well, what happens if, I mean, is this pipeline that you built is a giant house of cards that will collapse the moment any input does anything weird? And then there's a moment of silence. It's like, well, oops, yes, sorry, hang on. So this is actually very common. And as I mentioned before, it could be a database that changes format. It could be that now we have missing values in the data that we were not expecting. We have extra values that we were not expecting, duplicate values, and so on and so on. And so that if we want to, so the obvious thing that one can do to make sure, I mean, the first thing that one can do to make sure that the code that they're writing is sort of correct is to write some tests. But now this is data that we're not expecting. So to test for this kind of mistakes, one has to be aware of the expectation that one has on the code. And this is not really necessarily easy to do because it needs to be aware of what the code is expecting and then write the corresponding test for this. And so this is where essentially we are trying to do some work on, so essentially taking out the, figuring out, making explicitly what the expectation that the code has. So I have a specific example that I want to use throughout the talk. Again, I don't know if it's readable, but I can go over it so that you can see what I'm talking about. But so this is essentially a notebook that I wrote. It's a screenshot of a notebook that I wrote. There are various cells, and I'm sort of running them in order here. No weird executions. What I'm doing is reading some data from a CSV file. So the CSV file contains grades. So it has a student IDs, the name of the student, and then the grades that they got for each quiz that they took in the year. Then this quiz grades are in sort of A, B, C, D, F letter format. So I want to convert that into some number. So I'm using this dictionary here to map A to a 4, B to a 3, and so on. And then I essentially take all the columns with the quiz names and then apply this conversion. So I change the letter grade into a number grade, and then I compute the mean. So I add a column to this data. So when I read the file, I create a data frame, essentially a table of data. So I'm adding a column to this table of data with the mean of the grades. And now I want to communicate their mean to the students. So I'm reading the emails from another file. So in this other file, I have the IDs of the students and their emails and the names, I guess. And so what I want to do is merge together with this join operation. I'm merging together the data that I read with the quiz values and their mean with the data that contains their emails. And then I just project away anything that I don't need. So just keep the email and the mean. And then these is the data that I will use to send all the emails to the students with their mean. So this is all fine. This works fine and so good. But now I wanted to just give you some examples of what can happen when data is not expected. So let's say now we have some missing values. So maybe a student actually didn't take a quiz during in the year, so they don't have a grade for that particular quiz. So now what happens is that if they don't have a grade, maybe I want to ignore the grade or pretend that there is not a quiz to be taken. So just consider the rest of the grades. But maybe I actually want to give the student a 0 for the quiz that she didn't take. So what happens in this code, if there is a missing grade in the data, what this code does is actually not consider that as a 0, but to consider it as not a number, so a missing value. And then when I do the rest of the computation at the end, essentially that quiz is not considered as a 0, so the quiz is just missing. So the mean is actually only computed with the quizzes that she has taken. And so now, since the other quizzes are better than the original data in which she had failed the quiz, so this was corresponding as not taking the quiz. Now instead, we're not ignoring that quiz, and now she gets a better mean. Result looks plausible. It's not the right result necessarily. Another example, we have a student that is very good, so they just got A in all the quizzes, and now when we are typing all the results in a file, we have many quizzes, and just we put one extra A by accident because, well, they're always A, so we just put one extra. Now what happens is that we still read the file fine, but essentially everything gets shifted in the reading. So now the student ID is sort of ignored. So the column ID now contains the name of the student. The name of the student now contains the grade of the first quiz. And so now, except for the first student, all the other students have a missing grade for their last quiz. So as a result, when I compute the mean, all the students will only have the mean that corresponds to the last two quizzes, and the first is ignored. So in this case, the Bob and Carol, the second and third student, have a better mean than they were supposed to. Last example, maybe we have some grades that were not expected because they have a different format. So maybe we have a B+. We were supposed to just store a B, but we stored a B+. Now this is not expected in the grade transformation. The only transformation that we expect is from A, B, C, D, and F to a number. B+ doesn't mean anything here. So this, again, is a quiz that gets ignored, thrown away. So now the mean is different because we're not considering that quiz again. So various ways in which the same code with different data can just sort of go wrong. This is really the motivation for this kind of analysis that we're working on. So the idea is really taking the notebook the notebook reads some data. We don't know anything about this data. And the idea is that based on what the code is doing with this data, we're trying to sort of reconstruct what is the shape, or what are the, well, reconstruct some information about the data that we are reading. And in particular, what kind of expectation, what kind of format this data has, maybe the values and so on. Yeah, so to simplify things a little bit, I will consider data sort of simpler kind of data, so tabular data stored in CSV files, so essentially tables. And even so, I'm considering other kind of data could be XML files or any kind of more structured data format. But this is already fine in the sense that it's already a multidimensional data structure. So we are already sort of analyzing code and trying to get information about some data structure that is a table. So it's already it has already some challenges. So I think this is enough for now. All right, so then, yeah, getting back to the example that I had, I don't know if I want to do this. Okay, I will skip this for now, and I'll get to ignore this. We'll get back to it. So how we build the static analysis is going to be by Abstraction interpretation. No big surprise here. So the way we build it is essentially in 3 steps. They're not one step after the other, but they're really 3 steps that we sort of iterate back and forth through. So the first step is really defining precisely the model of the software that we were analyzing, based on the kind of, we want to model the behavior of the software we are analyzing, but focusing on the properties that we care about. I'll make it more concrete in a second. But yeah, so we throw away any information that we have extra, and we just focus on the information that we need to prove a certain property or to extract certain information from the code. And this is what we call the concrete semantics. So it's going to be correct and complete, but not something that we can compute, that we can work with. So on top of that, this is where the abstract domains come from. So we do the actual abstractions, and we define all the algorithms, transfer functions, all the operations that allows us to analyze the program. And then finally, we're going to have to implement this in practice, targeting actual programs. And so then we will see if things actually work, or we have to go back, maybe refine the semantics, or maybe refine the abstraction, and so on. So I'll just give you a few words on the kind of concrete semantics we're working with. I don't want to show any formula here, so really just the idea behind it. So the typical starting point is really essentially executions of the program, so the traces of the program from the input to the output. And in addition to this, so what we're saying is that we are looking at the execution of the program and trying to figure out some information about the input data. So what we are doing with the concrete semantics, so what this model of concrete semantics does is really just a sort of imposing constraints. So every execution step that we are adding to our traces essentially restricts the kind of restricts the possibilities that we have for the input data. So at the beginning, when we are reading the data, we have no information on the data. So any possible file is possible. I mean, we know it's a CSV file, so it's going to be a 2-dimensional kind of thing, but we don't know anything else. And then we do some operations in the code. So we're just going to essentially throw away data that doesn't fit this kind of operations that we are doing. So this is really the model, and so it's a bit different from the usual, because usually you have traces and you have essentially you're reasoning about the values of the variable in the program. And now here instead we are doing some indirect reasoning, because we need to consider what the impact of each execution step is on the input data. So there is this sort of level of interaction to the input data that we have to keep track of. This is really just the main difference with the standard trace semantics. Okay, I won't say anything else about the concrete semantics. Now what happens when we want to actually do an abstraction of this? So this is the idea. We want to sort of collect constraints, or well, eliminate possibilities about the input file. So the kind of abstract domain that the analysis that we want to do will have to essentially give us expectations on the files, or maybe extract constraints on the files and so on. So for this, we have some sort of abstract domain, which is this data exploitation abstract domain, not very clever naming. But the idea is that, so we're going to have to collect some constraints on the data. So all the operations that we're going to, the code is doing will impose some constraints on the data. So we're going to have some abstract domains that will essentially collect the constraints on the current variables of the program, and let's say on the current variables of the program. And then, as I said, we have this indirect reasoning with respect to the input data. So depending on the direction in which we run the analysis, but let's say we run it forward, which is the easiest way to run it for most people. In that case, then we will have to also maintain some dependencies. We're going to have to keep track of the dependencies between the input data and the current variables in the program, so that we can essentially reconstruct backwards the constraint that we have on or retrace backwards the constraint that we have on the input data. I'll give you some more concrete examples in a second. I'll just zoom in on these constraining domains. These really are essentially any existing domain would work fine. So numerical domains, if you want to reason about the values of the input data, string domains, because often we have also string values. We have what you have seen in the example here, the example that I showed you earlier. We may have some data structures that we're manipulating in the code, dictionary, lists, arrays, and so on. So we do need some domains to reason about collections. We may want to reason about types of the data, so simple type domains. And then in the case of this data science code, we may also want to have some specific domains that are rather simple, but capture some specific information, like whether a value is not a number or number, whether values maybe in some column, in some field are unique or not. So let's say we take a column of a table, we want to figure out that, we want to know that all the values in that column are unique. We don't have duplicates or this kind of things. So let's now consider one example, very simple example of a column of a kind of expectation analysis. So what could be very simplest thing that we can do is figure out what are the expectations on the column names of our files. So in CSV files, these are called fields, in a table columns. So we want to figure out what are the columns that we have in our data file. So we could have string sets just to figure out what the actual string name is. We could have character sets to figure out maybe, I don't know if you've seen it exactly in the code earlier, but in the code earlier, I was selecting the columns starting with a Q because those match the quizzes. So maybe you want to have character sets to figure out characters that are in certain specific positions of the column names, things like that. And now, since we have essentially sets of strings or characters, then we're going to have some dependencies that essentially are going to be set constraints. So we're going to say essentially the values, the names of this. So we're going to track. I'll give you an example in a second, but just to give you an idea, we're going to track essentially string values or character information about variables in the code, and with the set constraints, we're going to be able to say which of these values actually apply to the input data. Let me make it more concrete with an example. I think it's easier. So let's say we are reading some data file. At this point, we don't know anything. We just know that there is a data file somewhere. No constraint whatsoever here. Now, okay, this particular data file is reading house prices. I think I took it from another notebook that I found online. And now we are, with what this operation is doing is taking essentially the sale price. So there is the sale price of the house, and we take the very expensive houses. So we are just throwing away all the rows of the data frame that have a smaller sale price than 1 million. And we're storing this into this X variable, X for expensive. So we're subsetting this data file, just taking a part of it and storing it somewhere. So now what we know from this is that in the original file, we definitely have the column sale price because we are accessing it. And then we have this dependency here that whatever names we find out about the data stored in X, they are the same names that actually are in the original data file. This is because we're just throwing away rows, we're not throwing away columns, so we have this sort of equality dependency. And this is what allows us to sort of backtrack any information that we find, backtrack it to the input. Okay, let's say now we want to compute the profit, so we're going to have some operation that computes a difference between the sell price and the buy price, and we store it in profit. Now, with this, we know that we're going to have the sale price column because we knew it already before. We have the buy price column because we're using it here. And now this profit column, well, we are taking this operation and storing it in this profit column. So in pandas, in these notebooks, when you store values in a column, the column doesn't necessarily need to exist already. So if the column doesn't exist, you're adding it with this operation. So what we can say is that we may have already had a profit column, and it has now been overwritten, essentially, things like that. Now, in the example that we were considering before, when we read, so this grades of the students, when we read the CSV file, we know that there is a grades file somewhere. Later on, we are changing the values of the quizzes from letter to number. So what we know is that there are some columns, at least one, with name that starts with Q because of this code, selecting the columns that start with Q. Let's see. Later on, we're reading emails. Now we are merging together the data that we stored in the variable df at the beginning. So the data comes from grades, the data that comes from emails is stored in ES. So whatever names we have in the union are the union of the names in the original data, in the grades file and the emails file. So later on, when we now project away just the columns with emails and mean, we know that the email column in particular, the mean column, I mean, I skipped it here, but the mean column was assigned by this assignment here, so we don't know if it was present or not. But here we are projecting away the email column, so we know that it must have been there in either one of the two files. So it's there, we don't know where, because we just know that it's in the union. Okay, so this is sort of so far so good, rather simple. Of course, things can get very complicated very quickly. So here, I mean, I don't want to go into details, but the idea here, we're reading a file, then so this is a table, and now we're essentially pivoting the table. So what happens is that we're saying, whatever values you have in this column, so maybe this C, Y, L are maybe variables that determine the names of these columns. So whatever we have in the column Y, we are using it now as columns for this pivoted table, and so on. Then we are maybe grouping by, so we are reading another data file, storing it in this right data frame, in the R data frame, and then we're grouping by the pivoted data using the column in this newly read file. So yeah, sort of messy situation. So we may need to evaluate these variables to figure out what the, so we know that all these columns are in the read data file, but we need to actually evaluate this variable to figure out what the actual column names are. And then, yeah, we know that this column exists in the R data frame because we're accessing it, but then we can have very complex dependencies because we know that based on whatever these operations are doing, this column must be in the grouped data frame, and so there's a missing non-empty intersection. But yeah, there is an intersection between the columns in the two data frames because we're grouping by data that comes from here and so on. Yeah. So overall, what it means is that we have to deal with very complex library calls, and we have to figure out all this about multidimensional data structures. So even with a simple column field names expectation analysis, things can get quite complex quite quickly. Now, just in the time I have left, I'll just maybe briefly mention another kind of, well, what happens when we make analysis a little bit more interesting, maybe a bit more complex. So let's say we want to reason about values. So we may want to reason about types. We may want to reason about actual value relationship between the data or the columns or whatnot. And maybe we want to reason about whether data is null, not a number, or number, and so on. So the dependencies that we're going to have to keep track of are maybe type constraints, subtype constraints. We're going to have numerical constraints that we have to keep track of, and so on. So the dependencies get, the more complex the domains are, the more complex the dependencies that we have to track are. So just to go over the little snippets of code that I had before, here we're, as I said before, we are sort of throwing away rows where the sale price is smaller than this value, only keeping sale prices over 1 million. So now with this, we know, for instance, that the sale price column has a numerical value, should probably be an actual number and not a missing value, and so on. We may have maybe this numerical relationship between for the profit. So the value of the profit column depends on this other two values. And then, oh yeah, this is also interesting. So when we are pivoting, as I said, we are using the values of some column as the columns of the pivoted table. So now we know that the names of the pivoted table are the values of the column y, well, the column that corresponds to the variable I. So if we are able to reason about values, then we can also sort of make our column name expectation variable analysis more precise. Right. Good. Okay, and then this is the example, the sort of running example of this code. So this is what we got in terms of names. In terms of values, what we can say here, I'm using this pandas notation, but the idea is the first column of this data only contains unique values. This is because when we are reading the data, we have this extra parameter here that is setting the first column of the data file as an index. So it means that everything there should be not contain duplicates. So it's a unique value and should not contain missing values. Later on here, in the quizzes columns, as I said, we are mapping the quizzes columns through this dictionary that maps A to 4, B to 3, C to 2, and so on. So what we expect is that all the values that are in these columns are only A, B, C, D, or F, no other values. And again, there should not be missing values because of the operations we are doing on this. Again, here we are reading the emails file. Again, we are again using the first column as index. So again, the first column should be unique and different and not a missing value. not missing values, and so on. So we can get, here we are merging two data frames, well, two tables. And since we are not giving any parameter to this join operation, by default, it takes the index columns of the two data frames that are being joined. So in particular, we know that these index columns are the first ones of the two data frames that are being joined. So we know that the values in these two columns should be the same in both, and things like that. Okay, yeah. So this is sort of it to give you an idea of the kind of analysis that we are working on. Now, there are some considerations to make in designing this analysis. So when we want to sort of decide how we want to make it work in practice, and in particular, one thing that we want is to make this analysis usable by real data scientists. So we make a distinction essentially between the kind of expectations that we get. So there are some expectations that are necessary, and there are some expectations that are sufficient. So in a sense, necessary expectations are those that if we violate them, then they will definitely cause a problem. So in particular here, knowing that we have a column sale price is necessary because we are accessing this column. So this code will actually crash if the column sale price is not there. Here we are overwriting the column profit, so we don't care if the column profit was there before or not. So in a sense, we can just report things that we know for sure will make the program fail or create trouble. And so, yeah, these are the necessary expectations. And in a sense, it goes, I don't know if you know this paper, but it goes in the same direction of this paper here. The main difference is that now we are dealing with input data, so multi-dimensional data structures, not just, so in here it was really preconditions about functions in the code, so variables in the code. Now we're dealing with the input data. So that's the extra bit of complexity that we're adding to this. But the idea goes in the same direction. We wanted the result of this analysis to be actionable and useful to this data scientist. The other direction are expectations that will not necessarily make the program fail or create errors, but there are expectations that are reasonable based on the way that the code is written. So in particular, essentially, all of them that I reported here are essentially this kind of reasonable expectation. So the fact that data is unique in this first column of grades, for instance, is not, nothing will fail necessarily if this is not satisfied, but based on what the code is doing, this is a reasonable expectation to have. Same for not missing values and so on. So what we are trying to do is essentially report expectations in different categories based on whether they're necessary or reasonable and so on. So that depending on how much time one has, we can look at all of them or just part of them, most important. So sort of prioritize them however way they like. Okay, now the last bit, how we actually implement this. And at this point, this is really mostly a wish list. We're working on it. So the main feature that makes this notebooks interesting is the fact that they're organized in cells. So in particular, what one can do is really write the code, run the cell, then maybe write some other piece of code, rerun cells in different orders and so on. So we want really the static analysis to be interactive. While one writes the code, we can run the analysis, and then maybe we need to backtrack a little bit and then rerun parts of the analysis depending on the changes in the execution and so on and so on. And so it has to be fast, return results quickly, because they are really interacting with the files. So it has to be quick, and it has to be updating itself based on the execution that is being run or analyzed. The other thing is, in these notebooks, most of the time we're using Python code, but actually the platform is often used mixing other kind of code, like R is often used in this notebooks, and it's not infrequent to have Python and R all together. So we need to support different kind of languages separately and together in the same kind of file. And the kind of assumptions that one gets from one kind of code and the other are different. So that also makes it interesting. And then the last bit is, well, we're dealing with dynamic languages, so things are not easy in that sense. So what we want to do is to, I mean, the obvious thing is to combine it with the dynamic analysis, but we want to do it in a bit of a different way. In the sense that, well, if we just take the dynamic analysis, so we take data, we run the code, this is going to be essentially an overfit of the program. So what we want to do is essentially take an execution and sort of generalize it using an abstractions. And now, based on this generalization, we have some assumptions that cover this particular kind of, well, not this execution, but all executions that have the same assumptions of this single execution that we have observed. And now the point is which execution to observe next. And so the idea is that we want to have some sort of framework to reason about what kind of coverage we get with this sort of generalized dynamic execution, so that we can go to the next execution and get as close as possible to a, well, a sound result. This is sort of, yeah, the wish list that we are working on. Then finally, as I promised at the beginning, I would go back to maybe the example on the unused data. So this is another very common problem, data that is intended to be used in some way, but by some mistake is not. So maybe it remains unused, or maybe it's duplicated, or maybe when merging data, things get messy because we expect some merging behavior, but we get something else. So anything that has to do with data usage is also another kind of thing that we're working on. In particular, well, we had a framework a long time ago. I worked with this one with Peter Miller. So we had a framework for reasoning about, well, figuring out which data remained unused by the program. So we had a concrete semantic model, and then we sort of proposed some abstractions and showed that other existing analysis would actually also fit in this framework and could be used to reason about data usage, although with less precision. Later on, a couple of years later, what happened was that I took actually, so all this is again on this sort of pre-processing data preparation phase of machine learning data science pipeline, if you want. What I did later on was actually look at the end of the data science pipeline, so taking trained models, neural networks, for instance, and look at what it means to reason about data usage in that context. So I took the same concrete semantics model and used it to reason about data usage, for instance, for neural networks. And so we developed a static analysis for fairness, for proving fairness, verifying fairness, so that the classification made by the neural network is fair in certain conditions, or in certain target subset of the input space. And then it turns out that actually this kind of property is also useful. This was a collaboration that we did last year with Airbus. So it turns out that this kind of property, reasoning about data usage, is actually useful also in a safety critical setting. So they're experimenting with various models of neural networks for approximating, so as surrogates. So they have simulators for certain operations, and so these simulators are just too bulky, too heavy. They cannot be embedded on airplanes. So what they're experimenting with are surrogates, neural network surrogates for this. So they have some specific properties that they, of course, they need to verify. So they have the concrete simulator, and they know the expected behavior of the surrogate model. So they know it, more or less, the kind of properties they want to verify about this model. And one of the things that they wanted to verify was in particular that in certain conditions, if some sensors were faulty, they should not impact the result of their neural network surrogate. And this was exactly the kind of data usage property that we were looking at in the context of fairness for neural networks. So we essentially applied our framework with some slight modifications to their problem, and this was actually yeah, it worked very nicely, and we could certify their things and so on. Yeah, so we are continuing to work on the data usage space. What we are trying to develop now is well, generalize this concrete semantics, concrete modeling. Concrete model to actually reason about the impact of some more quantitatively, if you want, the impact of some input on the output. So data that is completely unused will have no impact, and data that is used may have more or less impact on the result of the computation. So yeah, we're trying to develop analysis and abstractions on this. Okay, this is all I think I had to say. Thanks a lot. I'm happy to take any questions, comments, remarks. If you want to collaborate, if you have students that want to do internships, I'm happy to welcome them, host them here, and so on. Thanks.
Any questions?
So my question is, sorry, my name is Mukesh from University of Cambridge. So my question is, have you had this experience that your analysis said that this program is right, but still when you run that Python code, it gave you unexpected result, and you tracked it back to a bug in some Python library?
Oh, no. So no, we haven't we haven't found anything of that kind yet. But it is possible that, so especially when we just focus on necessary conditions, it's still possible that we satisfy the necessary conditions, but the program still does something wrong, just because maybe the analysis wasn't precise enough. So we find only some, so we sort of under approximate the necessary conditions. So we find only few of the necessary conditions. So we're anything we don't find can still create a problem in the code. So yeah, it's possible. Maybe because the analysis is imprecise, or maybe because of the code is doing something that is actually should not do. But yeah, depends. But we haven't found anything yet. I mean, the implementation is really more of a wish list kind of situation at the moment.
Thank you for a really, very nice and lucid presentation of the problems with data analysis. Now, the one issue I see here is that the error reporting could be a nightmare. I mean, you could have mistakes in the data, you could have mistakes in the pipeline, there could be mistakes anywhere kind of in the pipeline. And, like the example you had about the mean. Now, how do you know that's not the right definition of the mean if there's a missing value, for instance? I mean, this sounds like it could be challenging in terms of getting accurate error reporting.
Yeah, so it's really, this part is not easy. So a lot of all this realm about reasonable expectations, it really depends on the application or the way the code is. I mean, there are a lot of heuristics that get into play there that seem reasonable. And then, the rest is going to be sort of talking with these people in some way and trying to well, okay, one way that we want to do it is to make it sort of tweakable so that one can well choose the kind of behavior that they want. But yeah, there are several parameters that one can set, and maybe they don't know what they want to set. So yeah, this is a challenge. I don't have a good solution. We have some sort of well, yeah, some of the reasonable expectations come from basically looking at what the code is doing and what this kind of code is usually doing. So yeah, maybe it could be some I don't know, crowdsourcing of the code over GitHub to figure out what's the right pattern of things to do. But yeah, I don't know. We're not there yet.
Yeah. So another question I have is about the sensitivity analysis that you talked about for fairness and for the kind of whether you're relying on failed sensors. Can you say a little bit more about that? How do you achieve that?
Yeah, so this one is really something we are working on at the moment. So nothing is defined yet. We're working on the concrete semantics. But yeah, the hope is to essentially use, so one example that I have is maybe if you figure out that you have some data that is more, so there are various, okay, the way I want to do it is to essentially, ideally, hopefully long-term, to reason about across the whole pipeline. So in a sense, taking the data preparation and then the model, the trained model at the end and so on. So if you maybe analyze, there are various techniques to figure out the or the more important features in a trained model, for instance. Let's say I don't know, a neural network, but it could also be a support vector machine or doesn't matter. So let's say you have some features that based on some standard techniques turns out to be the more important ones for a certain classification. And then going back, you realize that in your analysis, you realize that certain of these features are those that actually have more impact on the computation that is being done. And this earlier on, where these features are coming from is actually maybe sensitive data. And this is a problem in a sense. So the idea is we want to relate the input data with the result and figure out if there is problem in the way that the data is used that maybe introduces bias or introduces problems in whatever way. The way the analysis currently is set up is not set up, but what the semantics is doing is really we're trying to reason about what happens if we change the value of a variable. So we're trying to model it this way. So if we change the value of a variable and the output changes by a lot more than another variable, then we say that this first variable has more impact than the second. But yeah, this is really a develop of concrete semantics. And then the way we abstract it, I don't know yet.
So it's similar in some sense to the kind of information flow analysis.
Yeah. So the data usage in a few slides. Well, okay, I don't have the slides out anymore, but yeah, we did show that in information flow is actually one abstraction of this data usage framework. And now we want, but this was really just public or non-public, and then the way I want to do it is now generalize this to a more quantitative kind of thing. So figuring out which of data has more or less impact. So maybe a quantitative information flow kind of framework would also fit into this whole framework, I think, yeah. In the same way that the basic information flow fits in the data usage one. Thanks.
Thanks again for the talk. And if you were here, you could join us for coffee. But,
no.
And thank you for being a real trooper and
yeah, no problem.
Just the timing. Thanks a lot, Caterina.
No problem. Thanks.